To go through a chi-squared example. So I have a problem here from the homework. Remember, the chi-squared goodness of fit test is a test that determines how well our observed data matches some expected distribution. So for this problem, we're going to be comparing when people order food for delivery compared to what we expect. So there's an actual set of values here, and we're going to compare that to some values. In the background, it's also the same thing as comparing the percentages of each day. And so often we'll be given percentages here. So the null hypothesis is automatically that the data fits the expected distribution, and the alternative hypothesis is that the data does not fit the expected distribution. We might have to reword those for the problem. There is a way to write this with math symbols, if you are curious. It is not commonly written down, as it is somewhat difficult, but it would be saying that each percentage matches what it shows up. So this is kind of an extension of a proportion test that allows for more than two proportions to be compared. In an earlier chapter, we compared two proportions to each other. And right, the chi-squared test statistic that we calculate is a little bit different. This is somewhat similar to the idea of a z-score, though. We calculate a difference and divide to give it a standardized type of value. But we calculate this for each category, and then we add those all up. So that ends up being your chi-squared test statistic. A chi-squared goodness of fit test is always a right-tailed test. So we are always going to make sure we find the p-value using a right-tailed test. In Excel, the formula for finding the p-value, we can actually use a small shortcut, chi-squared dist.rt for right tail. And so we'll give it our chi-squared test statistic, and the degrees of freedom for the test is the number of categories minus 1. So for this problem we have days, so there will be 7 days, and the degrees of freedom is then that many days minus 1, so 6. Okay, so our alpha for this problem is going to be 10%. Let's look at the expected distribution already. So this is the expected percentages of ordering delivery food. So we can see Sunday, Monday, and Tuesday have very low percentages. Wednesday through Saturday have the most. Maybe that seems right. So the research firm is claiming is that the percentage of people who order delivery is not the same, is different than the pie chart. So maybe this pie chart was previous information and they think it's no longer correct. They're not giving us that exactly. So they have 494 people surveyed and recorded which day of the week they got delivery on. And so we're going to go through and compare. Okay, so our null hypothesis is going to be that the data fits the expected distribution. The expected distribution is this pie chart here. So it's going to be deliveries fit the pie chart data. We don't quite know where that pie chart is from. The alternative is going to be that the deliveries do not fit the pie chart data. Okay, let's see how they worded that. So the distribution of days people order food for delivery. So the null hypothesis should be that it fits the pie chart data, which is the expected distribution for this problem, is as shown in the pie chart. So that's what we said, a little bit fancier. The distribution of days people order food for delivery is different. So differs from the expected distribution, which is the distribution given in the pie chart. So we have to make sure we separate the actual frequency data we get, the observed data, and the expected distribution. Right, which of these is the claim? So the research firm is claiming that it is different. So they are different from that pie chart. So they are claiming the alternative. Okay, so now we have all of our work to do to calculate the test statistic. So this was step 1. So step 2, so we have to find the observed and the expected values for each category and apply the calculation here and add them all up. That'll be our test statistic. So we can put our data into Excel. I'm going to copy it. Frequency is fine for a label, but this is our observed value. Right, we need to know how many total observations there are here. They happen to say that it's 494. We will verify that. There's a lot of decimals there. Okay, so now we need to calculate the expected. So the percentages from the pie chart, maybe we'll call it pie chart, told us what the percent we expect, but we need to eventually convert that to the actual number we would have expected. So let's get our information from the pie chart. So Sunday was 8%. I think I already have these set as percentages. Monday was 4%, Tuesday 7, Wednesday 12, 11, 37, 21. So the pie chart here, wherever this information is coming from, is telling us that on Sunday, compared to your whole week, you'd expect 8% of the deliveries to occur on Sunday. So there were 494 total. So we would expect 8%. Since this is already a percentage, it's already been converted to 0.08 whenever we do math on it in Excel, times, so 8% of the 494. I can select the 494, but then I have to be careful to dollarize that. So that I can properly autofill there. So 8% of the 494 is going to tell me how many I would have expected here. And we can see that this is close and it makes some sense according to the problem. So if there were 494 deliveries in a week, I would expect 8% of them on a Sunday, and that would be 39.52. Of course, these are whole number type data, right? This is discrete data. It's also categorical data. It's days that we are looking at. So this calculation doesn't quite make sense for it not to be a whole number, but we can just go ahead and leave it like that in our calculations. Excel is also going to calculate it more accurately than it's showing, but that's fine. So we'll fill that in for all the rest. So this is how many I would have expected per day, and we can see that they are close. Monday is almost right on. Wednesday is a little low compared to what we would have expected. Friday is also a little low, and Saturday is very high. So now to get the chi-square test statistic, we're going to calculate observed minus expected, square that, and divide by the expected. So our observed value was 43 on this day, Sunday. We expected 39.5. square that, and then divide by the expected. So this is the individual contribution to this chi-squared from Sunday. So we'll complete that, and then our chi-squared value is going to be adding all of those up. So again, this is comparing what the percentages would have actually been, and maybe let me write that down. So 43 divided by the 494, but we need that not to move, so we need to dollarize that. So here are the percentages we actually observed. On Sunday, there was 8%, and we had expected 8.7, and we had expected 8. On Monday, let me move this down one. On Monday, we expected 4%, and there was 3.9. Tuesday is quite a bit different. Wednesday is quite a bit different. And we can see that Friday and Saturday here are some of the most different. So did this week turn out like we expected? Right, and it would be, what is hard to tell here is if one of them moves from a Sunday to a Monday, it's going to adjust multiple percentages. So they do look off, but are they off enough that we can say they are not matching? So it can be difficult to do that. Okay, so now we are ready to find our p-value. So this is always a right tail test, so we can use the little bit of a shortcut, chi-squared .rt. So chi-sq.dist.rt, RT for right tail. So this is our chi-squared value, and our degrees of freedom is our number of categories minus 1. So we have 7 categories for 7 days, minus 1 will be 6. E to the minus 7 means the decimal place has been moved 7 times, so this number is very small. If we change it to a number, show some more decimal places, you can see this number is very small. Okay, so let's input our test statistic, 38, so 3 decimal places, 842. And our p-value, rounding to 3 decimal places, this is just still 0. And so, thankfully, every time we can test with a p-value, all of our decisions at the end all stay the same. This is a very small p-value. I don't even need to go back and look at alpha, but alpha was a large alpha of 10%. So we are going to reject the null hypothesis. Our p-value, which was right now almost 0, was much smaller than alpha. At 10% right now. Okay, we forgot to write down the claim. We did do it over here. So the claim was the alternative hypothesis, that the deliveries did not fit the expected distribution. And since we reject the null hypothesis, we are effectively crossing this option out and taking the alternative as our correct answer. Can I just highlight this here? So we are essentially crossing off the null hypothesis and saying the alternative hypothesis is the correct situation here. And the person was claiming the alternative. So they were right, so we are going to support them. So there is enough evidence to support the claim. Since we reject, there is enough evidence to say something, and then since the claim is the alternative, there is enough evidence to support that claim. So we're going to reject the null hypothesis. There is enough evidence, And this is just the claim in words to conclude that the distribution of days people order food for delivery is different than the expected. That is the alternative. So if we wrote in what the claim would be. We have one small check we could have done here. So the homework will ask you for the test statistic. But if we wanted to verify that we did this right, we have another version of the chi-squared function called chi-square, so chi-sq.test. And this one we only need to give it the ranges, so we can verify that we do our work correct. In terms of the homework, it won't give you the test statistic though. So our observed values were so it's going to say actual range. Our observed values were these ones here, and we calculated on our own the expected values here. So this will, if I have only needed to do the p-value, I could have used this and avoided the calculation in Excel. As we can see, we're getting the same p-value here, nearly 0. Let's show a few more decimals to show these are the same. So this can give you the right p-value, which can give you information about rejecting or not, but unfortunately we will need the chi-squared test statistic, so we will have to calculate this on our own. All right, looks good.